This talk is about sliding window aggregation in stream processing systems, where stream data items might arrive out of order and streams might be bursty. In this talk, we consider a stream a potentially infinite sequence of data. And to process such an infinite stream, most streaming systems will define a sliding window, which basically comprises the most recent data items up to a certain count or a certain time limit. And as new data arrives, it is inserted on one end of the window, the newest end, and the oldest data is evicted from the other end of the window. Now, sliding window aggregation aggregates all the current data items in the window by using a binary associative operator such as max count or min or Bloom filter. And besides associativity, in this talk we will not assume anything else in particular. The operator needs to be neither commutative nor have an inverse. This talk is about how to deal with the common case in the real world where streams might be out of order. So here we are assuming that data items are timestamped and that the newest arrival might actually not be the newest data item. It might be older according to its timestamp than what's already in the window. And we'll also assume that data items are arriving sometimes in bulk or departing in bulk. And this might be caused, for instance, by catching up after an outage. While there is prior work on sliding window aggregation, none of it handles the full generality of what this paper presents. The AMTA algorithm performs sliding window aggregation, but doesn't handle the out-of-order case. And while it handles bulks, it only does so during eviction, not during insertion. The Daba-Light algorithm handles sliding window aggregation very efficiently, but handles neither out-of-order arrivals nor bulks. The FIBA algorithm, again, is an efficient sliding window aggregation algorithm. This one actually has out-of-order support, but it doesn't handle bulks directly. And then finally, the data structure literature, which we were inspired by, doesn't concern itself with sliding window aggregation or out-of-order support. However, we did take inspiration from its bulk handling. This paper builds on the FIBA algorithm to provide efficient bulk evictions and insertions. The FIBA algorithm already provides out-of-order support. Specifically, our new algorithm has three operations. Bulk insert adds a bulk of ordered data items into the window. Bulk evict removes all data items with timestamp less than or equal to t. And the query function from FIBA remains unchanged. And this paper proves three theorems, namely that bulk evict runs in amortized O of log m time, bulk insert in amortized O of m log d over m, and query in worst case O of 1, where n is the window size, m is the bulk size, and d is the number of data items in the window that overlap with the bulk, in other words, the degree of how out of order the stream is. So let me briefly recap the data structure of FIBA. It's called FIBA because it stands for Finger B-Tree Aggregator. So in other words, we have a B-tree with keys and values. In addition, every node also stores an aggregate. And then there are fingers, which are just pointers to the oldest and the youngest leaf. And the trick in FIBA is that the aggregates aren't just aggregates of everything under a particular node, but instead are optimized for efficient insertions and evictions. So they are optimized for being efficiently computed close to finger. Here's the intuition behind the bulk evict algorithm. The first step of bulk evict is to conduct a boundary search that starts at the leftmost leaf, traverses up the spine, and then down to find where the eviction needs to happen. And along the way, it also enumerates the nodes on the path from the spine to the eviction point. The second part of the bulk evict is a pass up, shown in golden here, along the boundary to the node on the spine. And potentially it might actually go a little bit further, but that is guaranteed to happen rarely enough so that it doesn't spoil the algorithmic complexity. And this pass up does the actual eviction, so it throws away everything to the left. And then the third part of the bulk evict function is a pass down that performs some cleanups, and in particular it recomputes any partial aggregates that might have been modified. Now let's look at how the bulk insert algorithm works. The first step of the bulk insert is again a search that walks up, this time from the right finger, up the spine, and then down to the insertion point for the oldest data item in the batch that is being inserted, followed by localized searches for the next data item to be inserted and the next data item after that, and so on, until all the insertion points have been found. The second phase of the bulk insert algorithm is a level-by-level path up the tree that adds all the new entries. And then, of course, as you add entries to nodes, those nodes might overflow, and this path will will guarantee that this is still a valid B tree by splitting nodes as appropriate. The important thing for the algorithmic complexity of the algorithm is that the path up will combine work as soon as possible. And then the third phase of the bulk insert algorithm is again a pass down the right spine, which repairs any aggregates on the spine that might have been modified. Now there's one implementation consideration that is very important, because if we don't pay attention to it, then it could derail the entire algorithmic complexity of our approach, which is when bulk evict is about to remove m data items, then that implies that it actually removes order of m nodes from the tree, and eagerly freeing those nodes, eagerly reclaiming the memory for those nodes, would spoil the algorithmic complexity because it would take time O of m, but we want time O of log m. The solution is a deferred tree list. So we only eagerly free the nodes that are directly on the boundary, and then store their children in a deferred tree list, which can then be used for future allocations or disposal. Now, the paper contains extensive experiments along lots of different dimensions. Here in the talk, we will focus on just 3 research questions. The first question is, how does native bulk eviction alter the latency profile? The second is, how does native bulk insert alter the latency profile? And then third, if you have real-world data where the window sizes and the out-of-order degrees are fluctuating wildly, then how does the bulk insert and evict matter? So here are the experimental results for bulk evict. In this figure, the y-axis shows latency and processor cycles. So lower is better, and these numbers 2 to the 4, 2 to the 6, those are kind of in the microsecond range. Every violin plot in this figure shows a different algorithm, and there are 3 algorithms that natively support bulk evict. The first one, AMTA, is from Related Work, and the other 2, BFEBA and BFEBA4 and BFEBA8, are variants of our algorithm with different arities. And as you can see, these 3 actually have the best latency profile, as expected. We also performed throughput experiments. The numbers are in the paper, and it turns out that, again, our algorithm performs well on throughput for bulk evict. Now let's look at the latency effect of native bulk insert. Here we have 2 figures. The first one is for the FIFO case, where all data items arrive in order, and the second for the out-of-order case, where data items are, in this case, 1024 removed from the newest end of the window. As you can see in the FIFO case, our bulk algorithms are actually not the best, because algorithms that are optimized for the FIFO case actually perform better, even though they don't have native bulk support. On the other hand, those algorithms, DABA-Lite, 2-Stacks-Lite, and AMTA, just cannot participate in the out-of-order experiments because they just can't handle those streams. And so in the out-of-order figure, you can see that indeed the bulk variants of our algorithm outperform the non-bulk variants. Again, these latency numbers are also representative of the throughput numbers, which you can find in the paper. The third research question was, does it matter on real-world data with wildly fluctuating window sizes and out-of-order levels? As a real-world data set, we are using data from the New York City City Bike. And the 3 histograms at the top demonstrate that in this data set, n, m, and d, so the window size, the bulk size, and the out-of-order distance, fluctuate wildly across the run. Now at the bottom left, you can see a throughput chart. The y-axis shows throughput in million data items per second. Higher means faster, so higher is better. And the solid lines here are the bulk variants of our algorithm, whereas the dashed lines are the non-bulk variants. And as expected, the bulk variants are substantially faster. So in this data set with real out-of-order data and real bulk evictions, we see a real payoff. To conclude, our paper is about making sliding window aggregation more broadly applicable by allowing it to handle more real-world use cases. This talk elided a lot of details which you can find in the paper, such as proofs, such as experiments with Flink and experiments with 1 billion data items and various other experiments. And we made the implementation of our algorithm available as open source. Here is the URL where you can find it.